In this video, I'm going to show you how to calculate the amount in milliequivalents of an electrolyte in an IV solution administered over a specified time, and also how to convert the milliequivalents to grams, and we are starting right now. Hello, this is Dr. Danquah. And if this is your first time here and you like to learn pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. So let's get right to it. Now, the question here says you are requested to fill a medication order calling for an intravenous fluid for dextrose 5% in 0.9% sodium chloride injection and 40 milliequivalents of potassium chloride in a total volume of 1,000 milliliters. The intravenous infusion is administered through an IV set that delivers 15 drops per milliliter. If the infusion has to run at a rate of 12 drops per minute for 15 hours, A, how many milliequivalents of potassium chloride will be administered, and B, how many grams of potassium chloride will be administered. So let's do a quick analysis of the question. In the question, you've been given a number of terms. The first one is dextrose 5% in 0.9% sodium chloride injection. So 0.9% sodium chloride, it's essentially normal saline. So in the normal saline LVP or large volume parenteral, you also have some 5% of dextrose in there. Now, this is just telling us this 5% in 0.9% sodium chloride injection. That is just letting us know the vehicle in which the potassium chloride is going to be injected into. So that has a volume of 1,000 milliliters, and you're going to put in there 40 milliequivalents of potassium chloride. So in this 1,000 milliliter bag of dextrose 5% 0.9% sodium chloride injection, you have 40 milliequivalents of potassium chloride. Now you're going to take that 1,000 ml bag and you're going to run it at a rate of 12 drops per minute, and you're going to do that for 15 hours, and the drop set that you're using has a drop factor of 15 drops per milliliter. So the important information here is going to be the 15 drops per milliliter, the 12 drops per minute, the time, which is the infusion time of 15 hours, and then the amount of potassium chloride in milliequivalents, which is 40, and then the total volume that you have, which is 1,000 milliliters. So we're going to start off with A, which would be to calculate the amount in milliequivalents of potassium chloride that will be administered. So you could do this a number of ways. A really elegant way to approach this question would be to use dimension analysis, and that's the process we're going to use in this particular solution. So for A, we can start with the flow rate, which is in drops per minute. So that's 12 drops per minute. And if we divided the 12 drops per minute by the drop factor, which is 15 drops per milliliter, you're going to end up with the flow rate in milliliters per minute. And so when you're using dimension analysis, the way this will work is you're going to multiply this by 1 milliliter, because in each milliliter, it contains 15 drops. And what we just did here is very similar, or essentially the same as dividing the 12 drops per minute by 15 drops per ml. And you notice that when we cancel out the terms, because in dimension analysis, you cancel terms numerator to denominator, you end up with milliliters per minute. So now you basically have flow rate in milliliters per minute instead of drops per minute. Now, the other thing you want to do is you want to know how many milliliters you actually administered in the 15 hours. Because if you give all of the 1,000 ml, then you're basically giving the 40 milliequivalents. But if you give something less than that, then by default, you're not giving all of the 40 milliequivalents. And so you need to actually figure out how much you actually gave to the patient. And so what we can do here is now multiply this by the time component. And since we have time in hours, we want to convert that essentially to minutes. So we're going to use the conversion factor, that's 60 minutes. Is 1 hour, and so now the minutes will cancel out, and so you're in milliliters per hour. But notice you're running the IV set for 15 hours, so we're going to multiply this by 15 hours, and now the hours will cancel out. So the only unit you have left is the milliliter term, which is basically the volume you administered. So since we are using dimensional analysis here, we still need to multiply this by the amount of milliequivalents that we have for potassium, which is 40 divided by the 1,000 ml. But I just wanted you to know at this point the volume that we have. So to complete this dimensional analysis, there's one more thing that we need to do. We need to multiply this by the ratio of 40 milliequivalents divided by 1,000 milliliters, because that will let us know actually how much in milliequivalents that we've administered. But just to give you some perspective, if we multiply all the terms that we have right now, it will actually give us the volume that we've administered. So if you multiplied 12 by 1, by 60, and by 15, and then divided by 15, it will give you the volume that has been administered. So the volume, if you did a quick calculation along with me, will be 720. So we have given the patient 720 milliliters of the IV infusion at this point in time, which means we have not given the entire 40 milliequivalents. And so to determine actually the amount that we have given in milliequivalents, we're going to multiply all of this by 40 milliequivalents divided by 1,000 milliliters. So the milliliters will cancel out, and the only term that you have is 40 milliequivalents. So now, if you multiply all the terms in the numerator and divided by all the terms in the denominator, it will give us the amount of potassium chloride that has been given in milliequivalents. So what that will look like is you have 12 times 1 times 60 times 15 times 40 milliequivalents. And if you divided that by the terms in the denominator, which will be 15 times 1,000, then that is going to give you 28.8 milliequivalents. Now, to determine the amount in grams of KCl that has been administered, we are going to convert this 28.8 milliequivalents to grams, and we are going to be using the milliequivalent equation, which is mEq equals amount in milligrams divided by the molecular weight times valence. And when you take potassium chloride and you put that in an aqueous environment, it's going to dissociate into the potassium cation and then the chloride anion. And the valence is the absolute charge on either the cation or the anion. So absolute of positive 1 is 1, or absolute of negative 1 is 1. And so the valence of this compound is 1. Another thing that we need is the molecular weight. So molecular weight of potassium chloride is 74.55. And so now we can substitute these values into the equation, and the milliequivalents we are interested in is 28.8. So we have 28.8 equals amount in milligrams divided by 74.55 times the valence, which is 1. And so now you have milligrams being equal to 28.8 times 74.55 divided by 1, and that's going to be equal to 2,147.04 milligrams. But we need to convert this to grams, so you multiply this by the conversion factor, that 1,000 milligrams is 1 gram. So the milligrams cancels out, and you end up with essentially 2.15 grams. So we just took a look at how you can solve the question, and what I'm going to do right now is demonstrate how you can use artificial intelligence to either check your answer or actually use it as a means to study whilst you are trying to understand the concept. So to do this, we're going to use Bevinzey, which is your #1 AI-powered learning platform. And then once you are logged in, you want to go to services, and there are several models in here. And the one you want to pick for this activity will be the chat Bevinzey. So just click on that. And I'm going to paste the question in there. And for this, we're going to be using the advanced model. And just click on this icon right here and let the AI do its own thing. So we give it a few seconds, and in a few seconds, it should give us the answer. And that should be sufficient to either check your answer or give you a deeper understanding of what the topic is about. So now here you have it. It gives you step-by-step solutions. And so what it did is essentially what we did with the dimensional analysis. It's just that in this particular approach, it breaks it down. So you recall how we did the 12 drops per minute times 1 milliliter of our 15 drops. That's what this particular term is. So by doing that, you actually get the rate in milliliters per minute. And we talked about that in the solution previously. And then if you go through the entire process, it tells you the total volume. We also talked about that in the other solution. And it ends up with the same answer. Now, when you talk about part B, it also does it correctly. So this is a good way to check your answers or even use it as a tool to study or understand the concept. So I'm going to put a link to Bevinzey in the description, and you can go check it out for yourself. So I hope you found this video tutorial useful. If you did, be sure to like it and share it. And if you have any questions, just leave them in the comments and I'll get to them as soon as I see them. If you'd like to learn more pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. Thank you so much for watching, and I'll see you in the next video.